function is a suppose this is the first page. Have to briefly normally suppose r bar of k denotes Euclidean Euclidean domain. That is a Euclidean domain is x1 is x2 up to so on xn. Okay, such that ai is less than or equal to xi is less than or equal to bi. Okay, this is called is Euclidean domain in r power of k. So this is called is a k cell. This is called is a k cell. So next is this is a next is so k cell is example is k is equal to 2. K is equal to 2 is called is in k is equal to 2. This is k is equal to 2. We can do rectangular array. What is the rectangular? This is x1 comma x2 point. So this x1 point x2 point we know a1 is less than or equal to x1 is less than or equal to b1. a2 is less than or equal to x2 is less than or equal to b2. This is a rectangular array. This is k is equal to 2 in 2 dimensionally. So like this. This is now. So k is equal to 3 in 3 dimensionally. 3 dimensionally is x1, x2, x3. So this is meaning a1 is less than or equal to x1 is less than or equal to b1. a2 is less than or equal to x2 is less than or equal to b2. a3 is less than or equal to x3 is less than or equal to b3. Okay, this is a 3-dimensional array. So we have to like this. This is a 3-dimensional array. So like this. This is a parallelepiped. So now it is a k cell. Already I am telling me theorem in this page number 6.32. 6.32 it is called this 6.32 it is a the theorem topic is. So what is the theorem? 6.32 the page number is 60. The theorem is interval. This is a theorem is this is a theorem is 6.32 theorem. This is if a n is a sequence of a closed interval in R, capital R, such that in is superset of in is a superset of in is a superset of R is equal to n plus 1, n is equal to 1 to then intersection n is equal to 1 to infinity is n is not empty, In addition, the length of in is equal to then length of in is tends to 0 as tends to 0. Then limit n tends to infinity. This is n is equal to 1 to infinity is n has a unique point. So this is a theorem statement. We have to prove also. So this is a proof. In is equal to closed interval. This is a closed interval is called is. Now it is a closed interval. An comma bn point. Okay. Now he be the set of all. E be the set of all an. Small an is belongs to capital N. Obviously, E is a bounded above. Bounded above is called is any B is are bounded above any upper bound. So upper bound is a definition is x is equal to least upper bound of E. So any positive integer m and n. So this can be written an is less than or equal to am plus n is less than or equal to bm plus n is less than or equal to bm. What is the upper bound is called is bn is any upper bound. This is a bn is upper bound. Then list number is also it is a list number is highest number is also upper bound. So this is x is less than or equal to bm for each m. Also am is less than or equal to x for all x is belongs to im. So m is equal to 1, 2, 3 up to so on m. That is the meaning intersection of m is equal to 1 to infinity is im is not empty. Non-empty and not empty. So this is not empty. So this is a clear not empty order. Now first equation, the length of in. This is the length of in is a tends to 0 has tends to 0 for each epsilon greater than 0. There exists a positive integer n. So length of im is less than epsilon m greater than or equal to n is the first equation. So that is the equation. Now again, it's not clear. This is a second. So this second page is if possible let x comma y belongs to high is equal to 1 to n is equal to 1 to infinity is high n. That is called is that is x comma y is a subset or equal to high n. So for any m, so therefore the length of high m is greater than or equal to 1, greater than or equal to x minus y. So x, this is the contraction to equation 1. So therefore the length of high m is greater than or equal to, so mod of x minus y. This is a contradiction. This is a contradiction. This is a contradiction to equation. Hence, n is 1 to infinity. This is high m as a unique point. A unique point. So unique point. Okay. So this is now 6.33. So let high n is a sequence of k cells such that high n is superset of high n plus 1. So high n plus 1, n is equal to 1 to up to son n. The intersection of n is equal to 1 to infinity, high n is not empty. This is also theorem important, short answer. Since high n is a k cell, so high n is k cell, so kb is a any positive integer. Suppose high n is a sequence of k cells such that in subset or equal superset of in plus 1. Since in is a k cell, we can find k is intervals ij to the power of n, ij to the power of n. For j is equal to 1 to up to son k. So in r power of k, such that, so the high n, so this high n is equal to high 1 to the power of n cross high to the power of n cross up to son cross high k to the power of n. So like this. So it's a clearly. Now again, this is, so it is high n in superset of or equal to high n plus 1. So high n plus 1, I z to the power of n superset of I z to the power of n plus 1 for j is equal to 1 to up to son k, 1 to up to son k, and n greater than or equal to 1. So n greater than or equal to 1. So that is now we know that for each j, so this is each j, the set high j to the power of n is equal to 1 to up to son is a sequence of intervals such that I j to the power of n superset of I j to the power of n plus 1. That is, intersection is not empty. That is the intersection element, we can take a common element. X star of j is element of n is equal to 1 to infinity. Then I j to the power of n is a each j is equal to 1 to k. This is called as capital X star is equal to x1 to the power of star, x to the power of star, xk2. So this is capital X star is belongs to n is equal to 1 to infinity. This is high n. So that is n is equal to 1 to infinity. So high n is non-empty, is a non-empty. Next, this is a theorem is 6.34. The 6.34, every k cell is compact. Every k cell is compact. Every k cell is compact. So this is a k cell is compact is called is. Now let high is equal to what now? This is called is x bar. This is x bar is equal to x1 comma x2 son is xk is belongs to r power of k. So this is aj is less than or equal to xj is less than or equal to bj. What is aj and bj? This is a closed interval aj comma this is a bj. So this is j is equal to 1 to up to son k. This is a delta is equal to, that is delta is equal summation of j is equal to 1 to k bj minus aj is a whole square whole power of 1 by 2. So this is 1. For any x comma y in high, we have norm of x minus y is equal to, this is norm of x minus y, here expansion. This is a norm under root of x1 minus y1 is a whole square plus x2 minus y2 is the whole square plus up to so on plus xk minus yk is a whole square. Okay, this is less than or equal to delta. So less than or equal. If possible, let high is not compact in r power of k, net r power of k. So on r power of k. So like this. This is now r power of k. We have to r power of k. So this implies I n naught. This is I n naught subset are equal neighborhood of r of x star. This is the neighborhood of r of x star is subset r equal to g of alpha. Implies g of alpha. This is a contradiction to b. So assumption that I is not a compact rank. And see every KCL is compact. So every KCL is compact. So that is called is so KCL is compact 6.34. Second తర్వాత third. Second after third this is a wrong. Second after, so this is every KCL is compact is second. So remark that is called is the mistake is just is after second page. After second page is we take now. This is called is after second we got every KCL is compact 6.3.4. So after that we can do under root of 6.34 under root of x square plus y square. After the pages, that is a fourth page. So what is the fourth page is this is a point. Then there exists an open cover g of alpha for I in r power of k such that a finite collection of from a classes of I. So this is actually 4 in plus 3. This is the fourth page. Actually in third page, after second third page. So then intersect Aj Bj in divided into two equal parts in name Aj and Cj. Like this is an interval. So I'm taken this interval. We taken what is the interval Aj and Bj interval in dividing Cj. So what is now this is the divided interval is called this. So Aj comma Cj one interval, Cj comma Bj is another interval. So dividing the lines in parallel to the axis through Cj, we can discuss the KCL in I into 2 power of KCL. Then by equation 1, at least one those in 2 power of KCL, a call it on I1. It is not covered by the a finite subcollection G of alpha. The distance between of the for these vectors. So the diameter of I1 is equal to. So what is the equal to diameter of I1 is a delta by 2. This is a delta by 2. That is the diameter is delta by 2. So again, and I1 is not covered by the a finite collection of members of G of alpha. We need subdivided is I1 and continuous the process. We obtain a sequence the sequence of I of alpha. So this is a sequence In of the sequence of In of in KCL. So this is in KCL. So KCL with the following properties. First property is A. I is superset of I1, superset of I2, superset of I3. superset of I3 superset of I3 up to so on. In is not covered by the finite subcollections of G alpha. A diameter of in is equal to delta of I. So diameter of in is equal to, actually, what is the diameter of I? So this is I1 is the diameter is delta by 2. So what is the now next is in is the diameter is equal to delta by 2 square. I2 యొక్క diameter and also this is I2, I1 is the diameter delta by 2. I2 is the diameter is called delta by 2 square. This is in diameter is equal to delta by 2 power of n. So that is called is the in is equal to delta by 2 power of n is a diameter. So that is called is delta by I. For high is n is equal to 1 to 10. Then by condition A, we know that high subset of I superset of I1 superset of I2 superset I3 for n is equal to 1 to infinity. Then n is equal to 1 to infinity, high n is not empty. Assume a point x star is belongs to n is equal to 1 to infinity high n. Then x star is subset of in, subset of I, subset of u of alpha is g alpha, implies x star alpha g alpha for some alpha. Since g alpha is open, there is a neighborhood. Now open is neighborhood, this means nr of x star such that neighborhood definition, a set is contained a neighborhood. What is the open set? A set is said to be open. It is contain a neighborhood. And what is the G alpha is a open cover. This is an open set. Open set undalante. What is the definition is called is? The definition is called is. So what is the definition is? So the set is containing is neighborhood of X star is containing G alpha. What is the G alpha is? Open set. The G alpha is an open set. The open set definition is containing a neighborhood. Choose a natural number L0 so large so that delta by 2 power of N0 is less than delta, less than smaller. Then for any y belongs to high N0, so high N0, so the C condition that is called is norm of x0 minus y is less than delta by 2 power of N0 is less than smaller. So y is belongs to neighborhood of in x star. So that is the x star. So next page you see it is also. So that after that this is now in third page. So this is hence implies. This is a hence implies. So this is implies is the third page is implies is called is. So implies. So IN0 is subset of NR. IN0 subset of NR of X star. NR of X star subset of G of alpha. So implies that IN0 is subset of G alpha. This is a contradiction to B. Our assumption that I is not compact is wrong. Hence every case cell is compact. So is a remark. So that is a remark is since every closed interval in R power of n is a one cell. Every one cell is compact. Definition. A subset E of R power of k is said to be bounded if there is a constant M. What is a constant M? What is the definition is a bounded definition? So that is a bounded definition is norm of X less than or equal to capital M, less than M. For all X is belongs to he. He is a bounded if and only if there is a neighborhood. He is a bounded. There is a neighborhood. He is a bounded. There is a neighborhood. N M of 0 of origin belongs to R power of k such that E subset of n of m of 0. So 0. For each neighborhood n in R power of k, we can find a k cell I such that n subset of I E is a bounded in R power of k. There is a k cell is I such that E subset of I is a definition. So after that, this is the 3. So the story. So that is the last page. I will. This is the last page mistake. So I'm to, this is the page. The theorem 6.25. 6.25 is called this. And for a subset E of R power k, following properties are equivalent. E is a closed and bounded. E is a compact. Every infinite subset of E has a limit point in E. So this is the 3 are equivalent. A, we shall prove that A implies to B. So what is the, we shall prove that? So A implies to B. We shall prove that A implies to B. We shall prove that A implies to B. That is called is, we shall prove that A implies to B. So we taken. We shall prove that A implies to B. So this is E is a closed and bounded subset of R power of K. So this is the theorem. E is a subset of, so this is E. We shall prove that A implies to be E is a closed and bounded subset of R power of K. Since E is a bounded, so bounded. So by definition of there exists K cell such that what is the previous E subset of J. E subset of. Since every K cell is a compact and every closed subset of a compact set is compact in 4.0, so we get is compact. So hence A implies to be completed. We shall prove that B implies to C. So we shall prove that B implies to C. So this is a B implies to C. Since suppose he is compact, then by previous theorem 4.3.10, if he is can be infinite subset of compact set Ki, he has a limit point. We now come to again in fifth page. So this is a in fifth page. This is a fifth page. So we got is is a limit point in K. Every infinite subset of K has a limit point in E. Now we shall prove that C implies to A. I think so. Limit point he completed B implies to A. Now we shall prove that C implies to A. E subset of R of K be such a point such that every infinite subset of E has a limit point in E. We prove that E is bounded. So if possible, E is not bounded, wrong sentence. Then for each natural number small n belongs to capital N, there exists Xn, and there exists a sequence Xn. So this is called as there exists a sequence Xn. There exists a sequence Xn is a belongs to Xn such that the mod of Xn is greater than N. So N is equal to 1, 2 up to 7 infinity. S is the consist of these points X1, X2, Xn. So then S is a infinite subset of E. So but has no limit point in R power of K and hence no limit point in E. For if Y belongs to R power of K, so then there is a natural number small n belongs to N such that N minus 1 is less than or equal to mod of Y is less than N. So let delta, so this is a delta is equal to N minus of mod of Y is greater than 0. So that is called as N delta of Y has a no points of S. So that is Xn minus of Y is greater than or equal to mod Xn minus of mod Y. So this is a greater than or equal to, next is, so is a greater than, so that is a greater than N minus of mod Y. N minus of mod Y is equal to delta. Now, and therefore, Y cannot be a limit point of S. Y cannot be limit point of S. So that is called is now. Now next is 2 times what are the, this is so this is called as but X naught is belongs to he also. S has no other limit point in R power of K. So that is Y belongs to R power of K. Y not equal to X naught. Then by taking delta. So what is the delta he's taking from? So this is the delta he's taking from Y minus X naught by 2. And natural number X naught. N naught is greater than 1 by delta. We have N is greater than N naught. So that is called mod of Yn minus of Y is greater than or equal to mod of X naught minus Y minus Yn of minus of X naught is equal to 2 delta minus of Yn minus of X naught. Okay. So this is called is greater than 2 delta minus 1 by N greater than delta. Though this is Yn does not belongs to N delta of Y. So N greater than or equal to N naught. So hence Y cannot be a limit point of S. So hence S has no limit point of in E, which is a contradiction. E must be closed. C implies to A is a, so he which is a must be closed. C implies to contradiction. C implies to C must be closed. C implies to A completed. That is a remark. What is the remark is called is, so this is the equivalencies of A and B in the theorem 6.3.5 is known as Hein-Borel theorem. So next is E is a closed and bounded if and only E is a compact. This is a theorem is asking the examination also. So this is easy like that. It is also 6.35 equivalence of A and B. Equivalence of A and B is called is a Hein-Borel theorem. So last theorem, this is called is 6.3.5. 6.3.5 is known as Hanen-Borel theorem. So is a closed and bounded. So like this. Next is 6.36. This is a 6.36 is. So what is a 6.36 is? So every Bolzano-Weierstrass theorem. Every infinite subset of E of R power of K has a limit point in R power of K. Suppose E is a bounded infinite subset of R power of K. Since E is a bounded, there exists a K cell in J subset of R power of K such that E subset of J. Since every K cell is compact, J is compact. Since every infinite subset of J has a limit point in J. Since E is a infinite subset in J, so now J, so it has a limit point in J. Since J subset of R power of K, E has a limit point in R power of K. This is the topic is 6.3. So next is the definitions is taken a continuity of a vector valued functions. A monotonic function lo we got a theorem. So we got a monotonic functions is I will explain what is a monotonic functions. This is a monotonic functions. What is a monotonic function? Suppose f is a real valued function in an open interval a comma b, then f is said to be monotonically increasing. What is a monotonically increase? A is less than, x is less than, y is less than b. Then f of x is less than or equal to f of y. So this is called this. This is A is less than open interval. F of xy less than or equal to f of y. So f of y. And f is x1 is less than or equal to x2. This implies f of x1 is less than or equal to f of x2. So is said to be strictly increasing, monotonically increasing at all. Strictly, so monotonically increasing. Monotonically increasing is called is x1 is less than or equal to x2. I think this implies f of x1 is less than or equal to f of x2. Said to be strictly is our monotonically increasing. Only strictly increasing x1 is less than x2. I think this implies f of x1 is less than f of x2. Or sometimes x is less than y. This implies f of x is less than f of y. This name is a strictly increasing. This is called this. What is now? So strictly increasing is clear. Strictly increasing. Now, okay. Strictly increasing is a function is a, this is the diagram is x1 is x2. This is called is increasing. Now it is called is f of x1. So f of x1. So this is called is f of x2. So this is f of x2. So strictly. So what is now? Now strictly decreasing. Decreasing meaning so decreasing is x1 is less than or equal to x2 same. So we have to definition f of x1 greater than f of x2. This is called is a decreasing, monotonic decreasing function. Strictly decreasing is function. This is greater than or equal. F of x is greater than f of y. Strictly decreasing. So monotonically increasing, decreasing. What is a decreasing is called is? This is a function decreasing. It's called is x1, x2. This is called is f of x1. This is f of x2. Okay. Strictly decreasing and increasing is also. Okay. Now it is a theorem. This theorem here, the textbook is the theorem is what of it is called is. So 6.7.3 in page number 67. 6.7.3 in page number 67 page number. This is equal from 6.7.3. 6.7.3. Okay, I am to read them. So it is also f be a monotonic function, monotonically increasing function defined on open interval a comma b. Defined on open interval a comma b. X is belongs to open interval a comma b with supremum of f. So this is supremum of a is less than t is less than x. F of t is equal to f of x bar and is a limit left limit. So f of x is less than or equal to is a right limit. F of x plus is equal to infimum of x is less than t is less than b. First supremum, it is a left limit point. The right limit point is equal to less than or equal to, it is equal to infimum. Okay, this is a infimum theorem, and it already in theorem statement. Now we have to prove. So this is a proof is, suppose s is equal to f of t. Suppose f is equal to f of t. So a is less than t is less than x. Then f of x is an, the name of this is called is f of t. A is less than t is less than x. So this f of x is called is upper bound. This is upper bound for s. F is monotonically increasing, hence a completeness axiom. Completeness axiom in BSc level. Real analysis a completeness axiom. F is upper bound for s. F is monotonically increasing. Hence, by completeness axiom, S has supremum. Say A. Supremum of S is equal to A. Supremum of S is equal to A. Now we prove f of x bar limit is equal to A. Epsilon greater than 0. The given greater than supremum of S is equal to A. A minus epsilon naught is not an upper bound for, is not an upper, is an upper bound for S. There exists A is less than T naught is less than X. So which f of T naught is belongs to S such that A minus epsilon is less than f of T naught is less than or equal to capital A. Now since f is monotonically increasing and A is supremum of S, we get A minus epsilon f of f naught is less than or equal to f of t less than or equal to capital A for all t belongs to t naught comma x. Taking delta is equal to x minus t naught is greater than 0. We see that t is belongs to open interval t naught comma x, or for all t belongs to x minus delta comma x. A minus epsilon comma less than f of t is less than or equal to A. So that is called is mod f of t minus A is less than epsilon for all t belongs to open interval x minus delta comma x. So this is a left limit, f of x bar is equal to A. Again, since f of x is an upper bound for S, and since A is equal to supremum of S, in supremum of S, we get A is less than or equal to f of x. So f of x. So hence we have proved that suppose A is less than t is less than of x, f of t is equal to f of x bar. So x bar is less than or equal to f of x is the first equation. Concerning the set S dash is equal to f of t is less than, x is less than, t is less than b. So we can prove it is also, f of x. This is f of x less than or equal to f of x plus is less than or equal to infimum of f of t, x is less than, t is less than b. This is a second. So okay, from 1 and 2 we get to supremum of. So from 1 and 2 we get to supremum of 1 and 2 get so supremum of. So it is called supremum. 1 and 2 we get supremum of. It is called is 1 and 2 we get supremum of f of t is equal to. So this is called is, so supremum of f of t is equal to f of x bar is less than or equal to f of x is less than or equal to f of x plus infimum of f of t, x is less than, t is less than b. So that is called. So it is a theorem is, next theorem is also is equal. Left limit also, right limit is also, left limit is equal to right limit. This theorem is also including 6.7.3. So f is monotonically increasing, if x is less than y, then f of x plus y. Monotonically increasing, 40, x is less than y. This is f of x plus is less than or equal to f of y minus we have f of x plus is equal to right limit angles f of x plus is equal infimum of f of t, infimum of f of t, x is less than t is less than b. So f of y minus this is a supremum of f of t. So a is less than t is less than x. Consider the sets. S1 is equal to f of t. So this is such that a is less than x is less than, that is a is less than of t is less than of b. So what is now so this is called this S2 is called this a is less than t is less than of first one is so sorry S1 is equal to this is x is less than t is less than of b. S2 is equal to f of t. So a is less than t is less than of y. So S3 is equal to, so x is less than t is less than y. So that is an intersection. S1 intersection S2 is equal to S. S is subset are equal to S1 and S is subset are equal to S2. So infimum of S1, infimum of S is greater than or equal to, and why it is now since. So yes, this is the definition. So we definition S subset are equal to S1 and S subset are equal to S2. That is the infimum of S is infimum of S1 and supremum of S. So is the supremum of S2. This is from 192 in general. Infimum of in general, every time infimum of S less than or equal to supremum of S. Infimum of S1 is less than or equal to infimum of S, less than or equal to supremum of S, less than or equal to supremum of S2. Infimum of S1 less than or equal to supremum of S2. What is the infimum of S1? F of x plus c. So that is f of x plus c. So that is called as f of x plus c less than or equal to f of y minus. Hence we proved. Now, okay. This is a not given limit to so this is f is said to be mapping is a unique limit point, the normal definitions. So next topic is uniform convergency topic is, that is a uniform convergency. Your textbook is So in page number, this is 208. 208 in page number, we got a 208. These are totally or definitions, interactions, uniform convergency, continuity, what like this. So it's a clearly next is Weierstrass approximation theorem, important in long question. Weierstrass approximation theorem. Weierstrass approximation theorem, this is a statement. So like that. So now this is a statement. Weierstrass approximation theorem. So Weierstrass approximation theorem we have to clearly before is what is a M test also, uniform convergence and differentiation.
Which chapter is this theorem?
Uniform convergence and continuity topic is a page number. So మీకు వచ్చేసేసి approximation theorem. This is the topic వచ్చేసి so 12th chapter. So 12th chapter, sequence and series of functions of Weierstrass approximation. Okay. So this is the page number introduction. See, we have to like uniform Fn is a positive pointwise like that. This is examples. Test of uniform convergence series. Now again, what is we learn uniform convergence power series. So after that, uniform convergence approximation. So uniform convergency, continuity and also these are continuities and also metric spaces and uniform convergency integration. It is also uniform convergency differentiation. So I have taken uniform convergency differentiation. So introduction student like this. Suppose Fn is a sequence of functions of differentiable and closed interval a comma b such that so Fn of x naught, a convergence for some point in x naught in closed interval a b. So అమ్మని వెళ్ళిపో చెప్తా. Suppose Fn is a sequence of functions of differentiable. ఫోన్ చేస్తుండే సంతకం ఒకసారి పొందావా ఇప్పుడు అయినా కానీ చూడు ఒకసారి. Such that Fn of x naught in convergence some point x naught in closed interval a b if f dash of Fn, this is called is f dash of n is a convergence uniformly and closed interval a comma b. Actually what happened is the differentiable. So what is the sequence? This is Fn of x naught is a differentiable on closed interval a comma b. Okay. Then Fn dash of n is also convergence uniformly and closed. Then Fn is a convergence. So convergence uniformly and closed. So that is f dash of x is equal to madam.
Sir,
limit
208 page లో Weierstrass approximation theorem
ఉన్నది దానికంటే కొద్దిగా డెఫినేషన్ చెప్పి డైరెక్ట్ చెప్తే అర్థం కాదని డిఫరెన్షియేషన్ టాపిక్ చెప్తున్నాను. సో దిస్ ఇస్ ద డిఫరెన్షియేషన్. మీరు చూడండి ఈ డిఫరెన్షియేషన్ మోడల్లో డైరెక్ట్. సో ఓకే ఇక్కడ చూడండి డైరెక్ట్ మీకు ఆ 208 అప్రాక్సిమేషన్ థియరమే చెప్తున్నానమ్మా. చూడండి అమ్మా.
ఓకే సార్.
చూడండి Weierstrass approximation theorem. ఇప్పుడు పేజ్ అవుపడదా యువర్ స్క్రీన్? Weierstrass approximation theorem. Your page number 208. 208 in page number long question. Weierstrass approximation. Your textbook లో తక్కువ ఉంటుంది. F is a real valued continuous function and closed interval a b delta greater than there exists a polynomial p such that ఒక polynomial p such that mod f of x minus f of f of x minus p of x less than delta for all x belongs to closed interval a comma b. కానీ ఇక్కడ థీరం స్టేట్మెంట్ వేరే ఉంటది, అంటే సేమ్ ఉంటది దాదాపు. సో వాట్ ఈస్ ద థీరం?
అంటే ఇది రాయొచ్చా మరి?
రాయచ్చు, నో ప్రాబ్లం, రాయచ్చు. అంటే if f is a continuous complex valued function and closed interval b, then there is a sequence pn. అక్కడ కూడా ఏమన్నాడు? పాలినామియల్ సీక్వెన్స్. అంటే ఇక్కడ సీక్వెన్స్ pn of a polynomials such that it is a convergence uniformly. So convergently uniformly and closed interval unto f naught. Further, f is a real valued, we can choose a pn to be real. So okay, now this is confirmed. ikkada only emanadu there exists a polynomial, so that is like, so ikkada proof, idantha proof adantha మీరు టెక్స్ట్ బుక్ లో తక్కువ ఉంటది, కానీ ఈ ప్రూఫ్ మీరు ఫాలో కావండి, సరిపోతుంది.
సార్ మీరు మెటీరియల్ పెడతారా సార్ ఒకసారి గ్రూప్ లో?
పెడతానమ్మా. సో ఆల్రెడీ పెట్టాను కూడా, గ్రూప్ లోకి వెళ్ళి తీసాను నేను ఇప్పుడు ఇది. సో దట్ ఈస్ ప్లస్ 1. ఓకే, వితౌట్ లాస్ ఆఫ్ జనరాలిటీ వి మే అజ్యూమ్ దట్. ఏం తీసుకుంటున్నామా? వితౌట్ లాస్ ఆఫ్ జనరాలిటీ, ఇది క్లోజ్డ్ ఇంటర్వల్ a కామా b. క్లోజ్డ్ ఇంటర్వల్ a కామా b ఏం తీసుకుంటున్నా? 0,1. సో ఆల్సో అజ్యూమ్ దట్ f of 0 is equal to f of 1 is equal to 0. Now consider a function. What is the consider? G is a consider a function. A 0,1 a closed interval 2 r is given by g of x is equal to f of x minus f of 0 2 minus x. Now that is f of 1 minus 0 less than or equal to x less than or equal to 1. Also, as f is continuous on 0,1, so g is with g of 0 is equal to g of 1 equal to 0. Is continuous అయితే ఏమవుతుంది? g of f of x is equal to ఏం తీసుకున్నాను? f of x minus f of 0 minus x తీసుకున్నాను. So that is, as f is continuous on closed interval, so g of 0 is equal to g of 1 is equal to 0. Okay, now in sequence, so this is a sequence. So what is a this is a sequence qn. Qn is a sequence of a polynomial such that if qn is a sequence of polynomial, this is called as now qn. So this is a qn. So like this, qn is a sequence in polynomial. Qn is converges to some g uniformly, and 0,1. So what is a pn of x in a polynomial is equal to qn of x in polynomial plus capital F of 0 plus x. So into into f of 1 minus f of 0. Now is a polynomial that converges to f of x uniformly on 0,1. In fact, limit n tends to infinity pn of x is equal to limit. What is the limit to pn of x is equal to? This is qn of x plus f of 0 plus x into f of 1 minus f of 0. This is the limit to pn of x is equal to, this is the limit of g of x plus limit n tends to infinity qn of x is equal to qn is a converges to g of x plus f of 0 plus x into f of 1 minus f. So these are constants. What are constant in qn of x anadi? It is a tends to g. Tends to g, and this is limit n tends to infinity in qn of x is equal to z. This is the g of x. Remaining all are constant. What is the constant? Is f of 0 plus x into f of 1 minus f of 0. That is called this. So further we define f of x is equal to 0 for all x is outside 0,1 closed interval, so that f is uniformly continuous on whole of f, the real line. So epsilon greater than 0 be given since f is continuous on the compact set 0,1. It is uniformly compacted, uniformly continuous on 0,1, and therefore is a delta greater than 0 such that what is a f of x minus f of y, so is less than epsilon by 2. This is equation 1. This is uniformly continuous for all x comma y is a belongs to closed interval 0,1. Okay, so mod x minus y is less than delta. Okay, also there exists m, capital M greater than 0 for all x belongs to 0,1 such that what is the bounded definition? F of x is also bounded. capital M greater than 0 అయితే బౌండెడ్ డెఫినేషన్ ఏంటిది? f of x is greater than a small m. Okay, this is equation 2. ఒకటి continuous and equation 2, 1 and 2. Now next, has a part of construction of the polynomial, consider the function. What is the consider the function is a polynomial is u of x 1 minus x square whole power of n minus 1 plus n x square. Then it is derivative. What is the derivative? U dash of x is equal, u dash x is equal to minus 2n x into 1 minus x square whole power of n minus 1 plus 2n. This is x is greater than or equal to 0 for all x is belongs to closed interval 0, 1. So u of x is a monotonical, u of x అనేది monotonical increasing, then function 0, 1 closed is a monotonical increasing 0, 1. Hence u of x is greater than or equal to 0 for all x is belongs to 0, 1. Now since u of 0 is equal to 0, we get u of x is greater than or equal to 0 for all x belongs to 0, 1, implies that 1 minus x square whole power of n minus 1 minus n x square is greater than or equal to 0 for all x belongs to 0, 1. This is a outside 1 minus x square whole power of n is greater than or equal to 1 minus n x square for all x belongs to 0, 1. So 0, 1. In third equation, this is a third equation already. So that is now we define in Qn of x. This is a Qn of x is a polynomial. Qn of x is a polynomial. What is the Qn of x is a polynomial? We take now Qn of x is equal to Cn into 1 minus x square whole power of n in fourth equation, where Cn is a constant. Choose that. So that is minus 1 to 1 to in Qn of x into dx is equal to 1. So for n is equal to 1, 2, 3 up to so on in 5. First we prove that each n so that Cn is less than root n. So from 4 and 5, 4th and 5th nunchi we prove that n is, so 4th and 5th nunchi we prove that Cn is root less than n. From 4 and 5 we get minus 1 to n in Qn of x into dx is equal to Cn minus 1 to n 1 minus x square whole power of n into dx. This is 2Cn. This is a integration. Limits change. What is the limits is 2Cn into integration 0 to 1 1 minus x square whole power of n in dx. 2Cn 0 to 1 1 root of n in 1 minus x square whole power of n into dx. We using 3 in greater than or equal to 2Cn. This is 0 to 1 by root n 1 minus n x square dx in greater than or equal to 2Cn 1 by root n into x cube by 3 root of whole power of 1 by root n. 2Cn this is 1 by root n, this is n by 3, so 1 by root n is a whole cube, that is called as cube chord, which is a, so it is a simplify that this is a 2Cn 1 by root n, limits applied, x cube by 3 ki 0 to 1 by root n apply, కాబట్టి ఓన్లీ ఏమొస్తుంది n by 3 into 1 by root n whole cube, 2Cn into 1 by root n minus n by 3 into 1 by n root n. This is 2Cn into 1 by root n. 1 by root n common this is 1 minus 1 by root n common say 1 minus 1 by, so 2Cn 1 by root n common this we got is nn is cancelled, 1 minus 1 by 3. 1 minus 1 by 3 is called is 2 by 3. We can do right here. This is a 2 by 3 part. So this is a 2 by 3 part. Okay.
Sir,
so like
1 by root n ఒక్కదానికి ఉంది కదా క్యూబ్.
1 by root n minus n by 3 into 1 by n root n. ఈ nn is cancelled. 1 by root n minus 1 by 3 1 by root n. 1 by root n కామన్ తీస్తే ఏమొస్తుందమ్మా 1 minus 1 by 3. 1 minus 1 by 3 అంటే what is the value? 2 by 3 root n. So 2 by 3 root n already ముందు 2Cn ఉంది. ఆ 2 ఏమవుతుంది 4 by 3 అవుతుంది. 4 by 3 ఓకే ఈజ్ ఈక్వల్ టు ఏమొచ్చింది టోటల్లీ 4 by 3 Cn by root n. This is greater than always Cn by root n. Cn by root n. Okay, na?
Okay,
Cn by root n. Okay. This is always Cn by root n, and always 1 is greater than Cn by root n. 1 is greater than Cn by. In take cross multiplication, we got is root n is greater than Cn. And what is the root n? And the 1 greater than Cn by root n. So in cross multiplication, root n is greater than Cn. Cn is less than root n. Cn is less than root n. This is a sixth equation. So it is called as sixth equation. Now, again, now for delta, is less than or equal to, now for delta. So this is, now for delta is less than or equal to, mod x is less than or equal to 1. We can squaring on both sides. Indirectly into the delta less than or equal to x. Indirectly into the x greater than or equal to delta. Squaring in x square greater than or equal to delta square. X square greater than or equal to delta square. So that Qn of x is equal to Cn into 1 minus x square whole power of n less than or equal to Cn. So 1 minus delta square whole power of n. So this is a Qn of x. This is Qn of x is less than root n, is less than root n of Cn value already telsu. Cn value less than root n. What this is less than root n into 1 minus delta square whole power of n is the seventh equation. In seventh equation, root n 1 minus delta square whole power of n is less than 0 as n tends to infinity. Qn of x is greater than 0 is uniformly for delta less than or equal to mod x is less than or equal to 1. This is Pn is equal to 0, 1. This implies 2 is capital R by defined by Pn of x is equal to minus 1 to 1 f of x plus t into Qn of t into dt. Qn of t dt. This is the eighth equation. So we got eighth equation. We show that we show that Pn of x is a sequence of a polynomials covering uniformly to f on closed interval 0, 1. And we show that Pn of x is in sequence of a polynomials covering to uniformly to f. Ekkada on closed interval 0, 1. Since I am to root of n into 1 minus delta square whole power of n tends to 0 as n tends to infinity, there is a natural number small n such that root of n into 1 minus delta square whole power of n root of n 1 minus delta square whole power of n less than epsilon by 8m. So for all m, n greater than or equal to n naught. This is a ninth equation. Now for n greater than or equal to n naught, x belongs to n greater than or equal to n naught. X belongs to, so x is belongs to 0, 1. We have this is mod of in Pn of x minus f of x. This is equal to mod. What is the limits? Minus 1 to 1 f of x plus t into Qn of t dt minus f of x into minus 1 to 1 Qn of t dt. So Pn of x value substitution, capital F of x value substitution. Okay. Now that is using this is the Pn of x value substitution and f of x value substitution. So we can do common. What is the common term? Qn of t. Qn of t is common. What of it is mod of minus 1 to 1 f of x plus t minus f of x is Qn of t into dt. This is a mod. Now is equal to mod. So this is a less than or equal to minus 1 to minus delta. This is mod of f of x plus t minus f of x. This is a Qn of t. So dt plus minus delta to delta. So mod of f of x plus t minus f of q n. So it is minus delta to 1. So ఒకసారి ఈ -1 to 1 ఇంటర్వెల్ ఏం చేశాను, దిస్ ఇస్ మైనస్ డెల్టా, దిస్ ఇస్ ప్లస్ డెల్టా, దిస్ ఇస్ వన్ ఇంటర్వెల్, దిస్ ఇస్ వన్ ఇంటర్వెల్, దిస్ ఇస్ వన్ ఇంటర్వెల్. అంటే హౌ మెనీ ఇంటిగ్రల్ టైప్స్? 3 టైప్స్ ఉంటాయి. వన్ ఈస్ ప్లస్, second is plus, like that. So copy how many integral part? I1 plus I2 plus I3, I1 plus I2 plus I3, the same in 10th equation. In 10th equation, so copy what is the I1 is equal? I1 is equal to -1 to minus delta, minus I1 is equal to -1 to minus delta f of x plus t minus f of x bracket qn of t into dt less than or equal to -1 to minus delta f of x plus t plus f of x is qn of t dt less than or equal to minus to plus. Equation 2 we get to I1 is less than or equal to 2m. 2m అంటే the totally bounded function got to 2m. So 1 to delta in qn of t dt. So this is called this in 11th equation. I3 is equal to delta to 1 f of x plus t into minus f of x t qn of t dt. So I3, what is I1 is a clear. I3, what is I3? 2m f of x is a bounded function, 2m delta to 1 qn of t into dt. So I1 plus I3 addition 2m, so -1 to minus delta qn of t dt plus delta to 1 in qn of t into dt. 2m is root n, 1 minus delta square whole power of n minus 1 to delta dt, so plus delta to 1 dt by 7th equation. I1 plus I3 less than or equal to 4m in root n, 1 minus delta square whole power of n in 1 minus delta, 1 minus delta is less than n, we have I1 plus I3 less than or equal to 4m root n, 1 minus delta square whole power of n. This is 13th equation. It is also already it is a 12th equation is called is I3 is called is a 12th equation. So I1 plus I3 adding, so by 7, so called it is called is in 13th equation. So 1 minus delta less than 1, we have I1 plus I3 less than or equal to 4m root n into 1 minus delta square whole power of n. This is a 13th equation we get by equation 1. So this is equation 1. So by equation 1, I2 is equal to minus delta to plus delta f of x plus 2 f of x in qn of t dt epsilon by 2 minus delta to delta qn of t dt epsilon by 2 minus 1 to qn of t dt epsilon by 2 minus 1 to qn of dt. It is a 14th equation. Minus 1 to qn of t dt is the value is 1. And it is a 14th. From 13th and 14th and 10th and then using the 9th. So to 13th and 14th and 9th by using in 10th, that is called is mod of n of x minus f of x is equal less than or equal to 4m root of n 1 minus delta square whole power of n plus epsilon by 2. So this is less than 4m, delta by 8m is plus epsilon by 2. So like this. So mod of pn of x minus f of x is less than epsilon. This implies that f of p, this implies that pn of x is converges to f of x, converges to f of x. So converges to f of x in uniformly on 0, 1 and 0, 1 in two cases. Second case, this is a second case is. So what is the second case is? In two cases are there in this theorem. This second case is, suppose capital F is continuous and closed interval where a comma b. So this is a comma b is not equal to 0, 1. So then the function s is mapping from 0, 1 to a closed interval a comma b defined by s of x is equal to a plus b minus a into x. So that is x is belongs to closed interval 0, 1, continuous and 0, 1 because s is polynomial. Since the function f is mapping from a closed interval ab to c, so and S is mapping from 0 to 1, 0 to 1. This is a closed interval a comma b to or continuous. The function g is equal to f circle of s. This is the mapping from 0 to 1 to c, where c denotes the complex plane, is also continuous. Hence, there is a sequence Rn of x. So this is a sequence is Rn of x is a polynomial such that, so that is a limit. The Rn of x is a limit. Limit Rn of x is equal to limit n tends to Rn of x is equal to g of x. So uniformly and 0, 1. To each epsilon, there is a natural number n naught such that n greater than or equal to n naught. So that is Rn of x minus g of x is less than epsilon. Rn of x minus f of s of x is a composite function less than epsilon. 15th equation. So for all n greater than or equal to n naught, x is belongs to 0, 1. Now we put s is equal to. So we put s is equal to. So we put s is equal to. So we put s is equal to. We put s is equal to. We put y is equal to s of x. X is equal to y minus a by b minus a. Y minus a by b minus a. Now in 15th equation, so we in 15th equation can be written as Rn of, this is 15th equation can be written as Rn of, this is a 15th equation can be Rn of y minus a by y minus b. So this is f of y, so is less than epsilon. So n greater than or equal to n naught, this is called y is belongs to closed interval a comma b. So Rn of y minus a by y minus b is equal to Pn of y, a polynomial. Hence Pn of y, hence Pn of y, it is also hence Pn of y, and this is called is much this is hence Pn of y minus f of y is a less than epsilon for all n greater than or equal to n naught. Thus Pn of y is converges uniformly to f of y. Hence the theorem is completed. Ante two cases lo, first case or second case. So in second case is also, suppose f is continuous, in first case is called as it is also without loss of generality. In two cases we have to prove is also, that is the theorem also, a uniformly converges theorem. Now where textbook lemma we have to write here lemma the 12.7.3 theorem మొత్తం 12.7.3 theorem is so we have theorem right here 12.7.3 theorem మొత్తం nothing but equal. So that is also case 1, case 2. Now in case 2 it is there. So okay, now so page number 199, the example is the convergence and differentials. Page number 199. 199, uniform convergence and differentiation. So this is called is uniform convergence and differentiation. This is a theorem. It is like that 12.5.2, 199 page number, 199 page number. So like this. Suppose Fn is a sequence of a functions of differentiable and closed interval AB such that Fn of x naught is a convergence for some point x naught in closed interval b. If f dash of n is convergence to uniformly and closed interval b, then Fn is convergence to uniformly and closed interval b. So f and f dash of x is equal to limit tends to infinity Fn dash of x. So that is called this. Now, this is a theorem proof also. Now, epsilon greater than 0 given since Fn of x naught. This is a sequence Fn of x naught converges to in closed interval a comma b. Some point x naught is belongs to closed interval a comma b. And f dash of xn. This is f dash of n is converges to uniformly and closed interval a b. So we can choose n1 is belongs to, we choose n1 is belongs to j for all n greater than or equal to n. Now mod of fn of x naught minus fm of x naught is less than epsilon by 2 first equation. N2 is belongs to j such that n greater than or equal to n2. That is the definition is mod f dash of m of t minus f dash of n of t. So this is less than epsilon by 2 into b minus a in second equation. Let n naught is equal to maximum of n1 comma n2. Then for m greater than or equal to m naught, n greater than or equal to n, the equalities of 1 and 3, equalities of 1 and 3. So that is called is equalities of 1 and 3. We can do right. So and the consider the function fm of f minus n fn, the point x comma t belongs to closed interval b, and applying the mean value theorem. Fm minus fn of x into fm minus fn of t mod of x minus t fm of fm minus n of, so that is a dash of c. So for some c belongs to closed interval a comma n is small n greater than n naught, small m greater than n naught. Equation 2 we have fm of x fn of x minus fm of t minus fn of t. So that is called is mod of x minus t epsilon by 2 into b minus a in the second a. So since x minus t is less than or equal to b minus a, fm of fn of minus f of t fn of t less than epsilon by 2 3. Again for m greater than or equal to n naught, n greater than or equal to n naught, x belongs to closed interval. We have fm of x fn of x is equal to fm of adding and subtracting minus fn of x minus fm of x naught plus ff of x naught minus fn of x naught plus n. So we have to less than or equal to rewriting this there. Fm of fn of x minus fm of x naught fn of x naught plus fm of x naught. So this is 1 and 3 and 4th equation given fm of fn of x less than epsilon by 2 plus less than epsilon by 2. So less than epsilon by 2 plus less than epsilon by 2. So it is epsilon. So f is a satisfy the Cauchy's criterion. Since Cauchy criterion is uniformly convergent, thus fn is converges to uniformly on f on closed interval a b. Limit n tends to infinity, fn of x is equal to f of x. A point x belongs to closed interval a b, qn of t is equal to fn of t minus fn of x by t minus x. fn of f of t is equal to q of t is equal to f of t minus f of x by t minus x. T not equal to x. Then for n greater than or equal to n naught, n greater than or, it is follows that q m of t qn of t less than or equal to epsilon by 2 into b minus a using qn of converges uniformly. Also we have limit n tends to qn of t is equal to limit n tends to f of t minus fn of x by t minus of x. Now limit n tends to qn of t is equal to q of t. Fifth equation. Further limit n tends to x qn of t is equal to limit t tends to x is fn of t by f of fn of t minus x. Limit t tends x qn of t is equal to f dash of x. Sixth equation. Now, limit n tends to infinity fn dash of x is equal to limit n tends to infinity t of qn of t. Limit t tends to infinity n tends to infinity qn of t. Limit t tends to x q of t using phi. Limit t tends to x f of t by f of x by t minus x is equal to f dash of x. Hence prove. So that is called is now. Okay, now this is a close. I am to and next Saturday I will take the class. So